Hello, my name is Petras Zdanavičius, and today I'm going to give a talk about Python integers. So let's start. What is an integer? It is a number, and the definition I found in Wikipedia was the set of integers consists of 0, whole numbers, and the additive inverses, which is a little bit confusing. So what I like this mathematical representation at the bottom, where you have 0, you have positive numbers going way to infinity on the right, and the negative numbers going way to negative infinity on the left. That's the small problem with the mathematical definitions and computers. The integers are infinitive set, and computers do have finite amount of memory. You cannot buy a computer with infinitive amount of memory, mainly because of blockchain. People are spiking up the prices of the hardware and the fact that actually such thing does not exist and it is just a theoretical concept. So what we have now is a computers with finite amount of memory, and we do need to compromise around how we store integers. And this is a C example. So nowadays computers are really fast. They have really fast CPUs and they can do really fast computations around integers, but only if you can fit the integers into CPU registers. Mainstream CPUs usually have the largest register in mainstream CPUs are 64 bits. Actually, there are larger ones, but the ones you can do mathematical operations are 64 bits. And this is, for example, in new modern languages like Rust and Zig, you usually don't deal with the type of integer, like abstract type of integer. You do deal with types like I16, I64 for storing integers in 62 bits. And in modern C, you usually don't use just integers to store data. You usually actually say like, oh, it's going to be integer 64, and so on. So as you can see, in 8 bits, the maximum number you can store is 127. You can store 255 if you don't care about negative numbers. And in 64 bits, you can store pretty quite large number. And day-to-day basis, you usually don't deal with larger numbers. So if you deal with smaller numbers, you can use 64 bits, and your program should be really fast because CPUs are really fast. For example, so C would compile it to machine code, and mathematical operations is going to be just one CPU command. In this case, for example, I'm including assembly code directly in C. So to add two numbers, or at this I'm subtracting. So to subtract two numbers, you only need one CPU instruction. Actually 4. One is to store number A into register, store number B into register, do subtraction, and move result from register back to some memory. So it's really fast. And let's compare that with Python implementation. Let's compare C and Python. Let me scroll that a little bit. No, I don't need to. Okay. So it's same code. It goes through 0 to 1 billion, I think. Yeah, 1 billion. And just adds it if it's even and removes it if it's odd number. So as you can see on my really old computer, which has native HDMI port, which is very ancient, C runs this code under 10 seconds. And Python runs this code, which is similar logic, like while, if, else. It takes 3 minutes and 47 seconds to run this code. So Python is really slow, except Fast API. Fast API is very fast. But it's really slow. And if some C++ programmer will start telling you that Python is slow, you should not do usual. You should not argue. You should say, yeah, it's slow. And know in your head, smile, and know in your head that you are working with much nicer language in probably much nicer environment. And let's be honest, probably making more money than C++ people. So just smile and say, yeah, it's slow. Plus, there's problems with C integers, and main problem is overflowing. So if you have, let's say, 8-bit integer, and you have maximum number, and you add 1, you would overflow. So CPU is not going to complain. The CPU is going to just add it, and you will get negative. So adding 1 to 127 is minus 128, which is not how math works, but this is how CPU works. So there is some unsafety and annoyance in using CPU integers. For example, there's some old game where you can defeat main boss, very powerful boss, simply by healing it instead of trying to fight it, thanks to integer overflow bugs. So, and Python integers do not overflow. Let's try if it's actually working. Oh no. Okay, it works. So it just works. You can write as large number as you want. And it just works. Right? So Python integers do not overflow. Why? Because it's not just like portion of bytes or number of bytes stored in memory. It's actually an object, because everything in Python is object. So how it's implemented in CPython? In Python 2, there were actually 2 integer types, int and long. Int was used for storing small numbers, and long was used for storing long numbers. There was a nice thing about Python 2. It would convert integer to long if it sees that the integer is going to overflow, which is nice, but it's also very complicated because all mathematical operations became very complicated. You need to check if it's long, it's going to be large, it's not going to be large. So in Python 3, integer object was removed, and only long object remained. At 2020, Python removed support for Python 2. So you could say that Python removed support for integers in 2020, which would be technically true. And let's move on. This is going to be the main slide. I have implemented this toy Python module that it's going to help me to investigate Python integers and demo how they look. So module name is, let's do some coding. So it's a very simple module. It has 2 functions, get parts and inspect. Inspect would update values on the right, and get parts we will use later. So let's investigate some random integer. Okay, so as every Python objects, C implementation has this header part, which is OB base. It has reference counting, which is 4. It has object type, which points to PyLong type. It has object size. And then it has custom data just for integer or a long object. It's obdigit. So as you can see, obdigit stores the integer itself. And all other is just for dealing with a Python and Python interpreter. Let's increase the number to see how it's actually. So now the integer is large enough, and as you can see in obdigit array, it's split into 2 parts. So this is how it's stored on memory. And its OB size is 2. Ref count is still 4. We will see later how to take that array of strange looking numbers. They have no relation to the number we actually inspecting at the first sight, and see how to convert it back. But now let's investigate some other numbers. So let's start with number 1. What's interesting about number 1 is ref count is 161. So there's 160 objects pointing to number 1. There's 2 things why it's so. So firstly, small numbers are cached in Python. So if you're using 1, you're using same 1 all over the place thanks to immutability of integers. And so it was used by Python environment to start Python interpreter, and that's why it was used 161 times. Let's look at number 2. As you can see, it's still a popular number, but not as popular as 1. And if you go further down the road, you're going to see the decrease in popularity. In integers, there's an interesting way Python implements negative numbers. So let's look at this number. Okay, and let's look at same number, but negative. The obdigit, the data array, remains the same. The only thing that changes is OB size. It becomes negative. So it's really interesting hack, but it works, so I guess it's okay. But you need to be aware that OB size of array could be negative. Okay, let's move on to get parts, and let's see how to take the numbers in obdigit and convert them back to what we're actually inspecting. Okay, let's use some nicer number. Okay, we are getting same array. We can work with it. it actually doesn't work like that. I know how it works, so I'm gonna write that, but I'm not going to explain it because you will see why. Enumerate. So we got the number back, as you can see in output. Why its formula is so strange? Multiplying by 2 is actually a shift operator. That's what it's doing a lot of shift operations. So this is the integer implementation in Python. Oh, I forgot one interesting thing. So I don't know if you know, there's this PEP42, I would dare say infamous PEP42, which claims you are not allowed to inspect number 42. You're allowed, but behavior is undefined. So let's actually do that. Oh no. I lied. If there is PEP42, it doesn't claim such nonsense. So thank you. If you have any questions, feel free to ask.
What is the reason for 2 to the power of 30 being the magic number?
So again, 2 power 30, so it means shift 30 times. Why 30? Python uses 32 bits to store like numbers into array, and one is reserved for signed, other is reserved for like actually doing. If you do operations, you need to add numbers, and you may spill into another digit.
But the negative number you showed that is actually indicated by the minus size. So why 2?
Yeah, but it's because you can if you multiply, you will overflow.
But you can use a signed integer.
That's right. I lied again. So I think it's just for like when you do operations on the items of array, they're gonna spill into like another bits you need to reserve. Is that answer your question? Not really. Feel free to navigate CPython source code.
Your example to convert numbers from parts, it doesn't work for negative numbers.
Yeah, that's right.
And how to make it work for negative numbers?
Just look at, so, okay, let's not do 42 anymore. If you run that, so it gets the absolute number correct, right? But I do not expose OB size in any of my toy module. So you would need to expose OB size as well. So you would need another method like get sign in addition to get parts.
Could you explain caching again? You mentioned there's caching involved, and is it integer specific or is it about objects, and like does it use a hash map? How does it work?
I don't know what it uses, but it's for integers specific. I think Python uses various caching mechanisms for other objects as well, but there is a specific like limit for integers that are cached. Maybe it's like around 200. I don't remember. But the usual suspects are cached.
The reference count is always 4 as you create a new number.
Yeah.
Why is that? Where do you get 4 references?
So sometimes it's 5. I think it's locals, globals. I'm counting it within function call, so function call stack, and like pointer itself I'm working with. But I lied one time, so I may be lying again.
You showed how many ref count has 1, it's popular, and etc. How popular is 0?
Let's see.
Okay, not popular.
Not popular at all.
You don't show just F count.
The price to give out. High performance by
So the rules are the same. I should give to the best question.
as you wish.
Okay.
You can ask your own question.
I think I'm first speaker that for me it's very easy to choose. I'm gonna give to the person who caught me lying, so. Okay, another question?
Can you try doing a float just for fun?
Do what?
A float.
Ah, okay, let's crash our slides. Ah, I was clever and implemented. But to show that it's actually, my slides are full of strange hacks, let's actually kill. It doesn't kill, because it dies sooner than assert false. It died. So thank you again.